Good morning, guys. We are looking at lesson 5.3. It's graphing exponential functions. I told you this is the meat of this unit, of unit 5, exponential functions. So our target for today, our goal is to be able to graph exponential functions and identify those key features. So an exponential function is a different type of line on a graph. It's not a straight line. So in order to graph exponential functions and identify those key features, we're going to need to identify the y-intercept. Good news is you already know how to find that. And then we're also going to need to be able to identify the growth and decay rate. We're going to need to identify both of those from an equation. So I'm going to show you where they are in the equation. We're going to need to be able to create a table of points on the graph, starting with the y-intercept. We're going to need to be able to plot the points and connect them to draw the graph. We're going to need to be able to determine the domain and range of an exponential function. And we're going to need to be able to write the equation for the horizontal asymptote. Good news, that horizontal asymptote is always the same equation in this class. So let's get started. So let's get started with this equation. We see f of x equals a times b to the power of x. Now, what are all those things have? In exponential functions, we don't have mx plus b. We have a b, but it's meaning something different in exponential functions. So let's first identify the a. The a is our y-intercept. That's where our y-intercept is going to be located on exponential functions. It's also known as our initial value. The b is our growth and decay rate. That's going to tell us whether or not our function is growing or getting smaller. So that b value, that's where we find our growth or decay rate. Remember, it's important to be able to identify them in just the equation. That's why I'm pointing these out for you right now. Now that to the power of x, that's still our input. That's our normal x, the input or the domain. Good news is x and y don't change when we're dealing with different functions. They're still, and x is going to still be our input or the domain values. And then the f of x, also known as y, is going to be our output or the range. So that is the equation. Main thing, a, that first number is going to be your y-intercept or the initial value, and then the b is going to be that rate, that growth or decay rate that you see. So let's talk about it. Exponential functions, where the exponent is a variable, right? That's why the x, it was to the power of x. The exponent is a variable. And again, let's just talk about what is a and what is b. Well, a is the y-intercept or the initial value. And b is that growth or decay rate. Super, super, super important to be able to understand what the a is and what the b is, so make a note of that. A is your y-intercept, and b is that rate that you're going to be growing or decaying by. Let's now talk about an asymptote. We said that's another important thing. It's pronounced asymptote. Okay, and an asymptote is a boundary line or just a line that a graph never crosses. Okay, so it's an imaginary line. And it's a boundary line. The graph's never going to cross it. That's why I said boundary line. But it's a line that the graph's never going to cross. So the exponential function is never going to cross this imaginary line. And asymptotes are drawn as dashed lines because they're not part of the original graph. They're just there to show you, hey, this is this imaginary boundary line that we're not going to cross. So what's the equation for an asymptote? Y equals 0. Always, always, always in this class, the asymptote is going to be y equals 0. Later on, you'll get to transformations and the asymptote can move. But for standard exponential functions, the asymptote is always going to be on the x-axis, where y equals 0. So now let's talk about growth or decay, because it's important to realize what is a growth value and what is a decay. And remember, this is when we're talking about the b value. So when our b value is greater than 1, so bigger than 1, the graph is going to be growth. It's going to be a growing exponential function, and it's going to look something kind of like that, where you're growing and it's not at kind of like a constant rate there. If the b value is a small number between 0 and 1, then the graph is going to be a decay, and that's going to look the opposite direction. That's going to go kind of like that. So that's your general idea. Growth is kind of going up and decay is going down, kind of the same way that you would think of positive and negative slopes. But then, but that line is kind of curved somewhat. So it's all in relation to the b value. Is the b greater than 1, or is the b between 0 and 1? Okay, so let's go ahead and look at this example where we're going to just identify the key features of the following graph. So on the graph, I have an exponential function. We're going to be able to make a table of points, and we're also going to be able to identify some things. So let's start with the y-intercept, that initial value. Where's the line cross the y-axis? Crosses it right there at the point 0, 6. So that's our y-intercept. That one's pretty easy because it's something we've seen before. Now we need to get some other points. Looking down to the right, those points get really small, so sometimes it's hard to find points. I'm just going to look for anywhere we have a nice pretty point. I see one right there at negative 118, and it looks like we have one at 1, 2. Okay, so from that, I'm going to go ahead and make us a table of my points. Now we're going to use this table to help us find our rate. We can find our rate by dividing y2 value by the y1 value. So in this case, our first y value is 18, and our second one is going to be 6. So I'm going to divide 6, my y2, by my y1, 18, and then I'm just going to simplify. And then that gets me to 1/3, which means my rate for this problem, my b value, is going to be 1/3. Okay, this is the important information right there. That's how you're going to be able to find the rate. So rate is 1/3, that b value is 1/3. Is that growth or decay? Well, is it greater than 1, or is it between 0 and 1? 1/3 is between 0 and 1. So that means we're going to have decay. Oops, still in the highlighter. I'm just showing you there. It's because it's between 0 and 1. Now, what's the asymptote? I told you the asymptote is y equals 0. And we could kind of draw a little dashed line if we wanted to on the x-axis. That line is never going to cross it. It's going to get really, really close. You can see towards the end where x is 7 and x is 6. It kind of looks like the line is on the asymptote. It's not. It's just really, 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 really close to it. Okay, but it will never actually cross that and go into this negative region down here. We'll never have an exponential function down there. So if we wanted to write the formula, we could. Remember that exponential functions look like y equals, or f of x equals a times b to the power of x. So let's just plug in our a and b. And we get, I'm going to erase that there, y equals 6 times 1/3 to the power of x, being our equation for that exponential function above. Let's talk about the domain and range now. The domain, well, if you notice the arrows, they're going to keep getting bigger. They're going farther out. Our domain, or the x values, is going to be all real numbers. We're going to keep increasing both to the right and to the left on all exponential functions unless there's a point that stops it. But if there's arrows, it's going on all real numbers. But our range for the y values, because we have that asymptote and it's at x equals 0, our range is going to be y values greater than 0, because that arrow at the top is going to keep going and going and going. We're going to end up with y values greater than 0, but nothing below that asymptote. Keep in mind that if our asymptote were to change, that would change our range. So always kind of look, where's the asymptote? Where's that line looking to kind of flatten out? That's going to be where your asymptote is, and the range is going to be all numbers above it. Or if for some reason the graph is reflected or flipped over and it's kind of on the bottom, then it would be all real number or y values less than 0, or whatever the asymptote is. Let's look at now these next two examples. So example number 2, it gives us the equation y, or f of x, equals 2 times 3 to the power of x. So how do we start? Well, we need to graph. So we need to identify that a and that b value. The a is your y-intercept. And remember, it's the first number. So that first number that's listed there is 2. So my y-intercept is going to be at the point 0, 2, which means I can plot a point on the y-axis at 2. We also know that my rate is 3. So my b value is 3. And that's going to help us in making a table. Because 3 is greater than 1, it's going to be growth. So we know it's going to be growing. It's going to kind of look something kind of like that. So on my table, I'm just going to come up with some easy points, -1, 0, 1, and maybe 2. As we kind of just work. We already know that when x is 0, y is 2. And now all we need to do is multiply by the b value to increase, to get our points for our table. So times 3. So our next point would be 6. And then times 3 again. And our point would be 18. And we work backwards to fill in any negative x value. So we would divide by 3. Going backwards there to find this missing one. And we would get 2/3. That's not a really pretty point, so we can kind of estimate that one, but we're going to use that to plot now the points on our graph. So here are all our points. We can kind of connect them there. And you can see that that is going to be our equation. That asymptote is going to always be y equals 0. Last example on here, y equals 8 times 1/2 x. So this time our a value is 8 and our b value is 1/2, which means it's going to be decay. So we set up the table, we're going to multiply by that b value, and we're going to use that to find the points. So again, I'm kind of just going to use the same x values this whole time. We know that that one is our y-intercept, and then multiplying by 1/2, so our next point would be a y value of 4, and then a y value of 2. And that means if we're dividing by 1/2, that's actually going to be multiplying by 2. It's going to be a little bit bigger. And we can use this now to come up with our points. We already know this is the y-intercept. And we know that our asymptote is going to be at y equals 0. So now let's just plug in those points. 0, 8, -1, 16, 1, 4, and 2, 2. So you can see it kind of has this nice little sloping pattern to it. That's what we call exponential, and it's going to keep going. Remember, it's not ever going to touch this lovely asymptote. Just like that. Okay, so that's a quick little introduction of exponential functions. A and B are super, super important. Okay, so making sure you understand what the A is, it's the y-intercept or the initial value, and the B is the growth or decay. Okay, and use graphs or use tables to help you graph, and then make sure you have a good understanding of what that the asymptote is and what domain and range are. Let your teacher know if you have any questions.